Yes, so I'm going to start with listing some problems that are kind of Erdos type problems, so in the discrete setting. And then I will tell about some analogues where instead of finite set, we take infinite ones, and instead of the cardinality of the set, we're in the Hausdorff dimension of the set. So I'm starting with the discrete setting. So Erdos problems. So the first one is actually a question of Elekes, not of Erdos. It's the same flavor, so it's about expanding polynomials. And the question is this: we are given a polynomial of two variables, it's a real polynomial, and we are given two finite sets of real numbers. So A, B are subsets of R. They are finite, let's say, of size n, so each size n. And what we are looking at is the image of A Cartesian product B under this polynomial f. So I will denote it like this. So f of AB is just sets of B. So FAB, where A is from A and B is in B. So if each of these sets is of size n, we consider here n squared pairs. So in general, we expect this set to have size n squared. But what if we choose A and B very carefully? Maybe we can have many repetitions, so that this set will be small. So this was the question of Elekes. So Elekes asked, one, choose and B, so that A is small. And in a paper from 2000 with Ronyai, so Elekes and Ronyai, they proved that for most polynomials, we cannot choose the sets FAB so that the image would be very small. What is small? So small would be linearly n. So let me write the statement. So that is polynomial. Then there are two options. So either for any choice of A and B, the image must be large. So what does it mean large? So Elekes and Ronyai showed a little omega of n. Later it was improved in a paper of myself, Shmerkin, and Sharer to n to 4/3, and recently the best bar now is n to 3/2 to Shmerkin. We improve the exponents to n to the 3/2. Okay, so this is one option, and the other option, so the only case where this is not true is when x has a certain degenerate form. So f is of the form. So I want to write x plus y, but if I take here a polynomial p of x, I can still choose here. So either this or p of x times q of y, where h, p, and q are univariate polynomials. if I don't insist on polynomials, then actually that's the same thing, right? I can take a log here and get the additive form. Okay. Okay. Of course, if F has one of these forms, then we can choose sets A and B such that the image is small, is linear in N. So we just make sure. So if F, for example, X plus Y, take A, B, this to be any arithmetic progression, and then the image size 2n minus 1, so linear in N. Okay, so the two options are excluding one another. Okay, so a slightly more general, let me erase this. Good. Okay, slightly more general result is the generalized is this one. So one way to think about this theorem is as if we take the graph of the function and we bound, now we are in R3 and we bound how many points of an n by n grid lie on this graph of the function. So
one question, like, is that statement like for almost every choice of A and B? Because can't I, like, if the degree of F is high enough, can't I just pick something so that it vanishes everywhere?
So again, you're asking about
yeah, the first half.
The first one is for any choice of A and B, but here you have, so here it means a constant times n to the 3 halves. So the constant can be large enough so that the degree wouldn't make any difference. So the idea is for large n. Yes. Okay, but it's for every. Yeah, maybe this notation is.
The constant depends on F.
On the degree or F only.
So the constant will depend on,
the
the degree actually, we can have,
sure.
right?
But it should
Yes.
depend, right?
Yes.
Right.
Maybe this is a notation of like, okay, so it's not, yes. Yes, but the exponent is independent of the degree, which is, but yes, let's, okay. So generalization of this result is following. So instead of taking a graph of a function, let's take a polynomial of 3 variables. No. Oh, yes. Thanks. Okay, that's important. I wanted to say that it's confusing, and here it's going to be an upper bound, and now apparently I did. But okay. Okay, so now we have a polynomial of 3 variables, and we are given n by n grid, and we want to say that in general, the zero set of this polynomial will not have too many points on this grid. So we have this. F depends non-trivially on each of the variables. Did I write it? Then one of the following holds, so either one or A, B, C subsets of R finite size n. So they don't have to be all of the same cardinality. It just simplifies the statement a little bit. But otherwise, there is an expression that depends on the cardinalities of A, B, and C. So no matter how you choose A, B, and C, the number of points of the Cartesian product n by n grid that lie on this surface that F defined is going to be small. So what do I mean by small? So Elekes and Ronyai showed n to the power of 2 minus some eta, and this eta is, they didn't give a concrete expression for eta, and they say it depends on the degree. Maybe the proof is something better, but say it depends on the degree. And with the recent improvement of Shoibushi and Zahl, we get here constant times n to 12/7. So the exponent. Okay, so this is one option, and the other option is more or less this, but this time we will have it only locally, and instead of polynomials, we will have invertible analytic functions. So locally, this looks like Qx plus Qy plus R of Z0. So I didn't write the second item formally. So if we will look at this surface at equals 0, we will have a sub variety where we can't say anything. But for any other point on this surface, we can take a neighborhood in R3. So this is a cube in R3. And every point here, you can tell whether it is on the surface or not by checking this condition. So PQR analytic invert, but it's not so important for this talk. So okay. Questions about this? Yes. The second comment that I want to mention here is Erdos distinct distances problem. So the setting is this: we have a set in the plane this time, so it's a finite set. Let's say of size n, and consider the set of distances that this set of points span. So delta of p will be on the pairwise distances of p is q, such that p and q. So similar to before, we have a set of size n. We consider n squared pairs, and we look at the distance that they span. In general, if you would choose p at random, we don't expect to have any repetitions. So this set will have size roughly n squared. Of course, if p equals q, we have many zeros. But Erdos asked, can we choose p in a very special way, such that the number of distances will be small? And he showed an example. So okay, so the questions are this. How small? So to write it formally, let's define delta of n to be the minimum over all sets of size n of cardinality delta of p. Okay. And it's like that. So what do we know? So delta of n. So Erdos gave an example of a balanced grid of size square root n by square root n, where the number of distinct distances spanned is at most constant. Whenever I write a constant, it's a different constant. I can write it like this. A constant is, in the example, it was a constant times n over square root of log n. And so this is Erdos. He conjectured that this should be right. And about 10 years ago, Booth and Katz almost completely solved it by showing that for any set, the number of distinct distances will be at least n over log. So there's still a small gap, but so this is good from that. Okay. One can ask also about the P inversion. So if we have a small number of distinct distances, maybe we can find one point that already see all those distances. If we check the distances between this point and the rest, maybe already we see many distances. So let me just give here just the notation because I will need it later. So when I write delta P of a certain set, I don't want, okay, I'll call it capital P. This is small p. What I mean is all the distances between, let's write P now, between P naught and Q, where Q is. So we fix one point and we look at all the distances. Okay. Okay, last question that I want to mention in the discrete setting is maybe an instance of this one. So distances, or a variant of this one, distances from 3 points. So here it is very similar, but we fix 3 points, P1, P2, and P3. And we're given a set P of size n, and we consider all the distances between these 3 points and the set P. So we care about, so P is in R2, and size n, and we consider, maybe let's write it as the union. So D would be the union of the distances between P1 and the set, the distances between P2 and the set, and the distances between P3 and the set. And so this time we have only 3n pairs, so the number of distinct distances would be at most 3n, but can we make it much smaller? How small can they be? So let's look at the picture and then I'll prove something about it.
3 as opposed to 2 or 5.
Okay, good question. So this is exactly what I'm going to show now. So let's say that let's start with 1 point, P1. And we have all the distances between P1 and the set P. So let's say that the number of this, so let's say the size of this set is T. So what does it mean? It means that one way to say it is that if I take the distances between P1 and this set is of size T, we can just take circles centered at P1. We need T circles for the discrete distances. And what we know is that the set P must be supported by the union of these circles. Right? So we'll have here somewhere points from P. And it will contain all of them. So this P is this feature of this. So P must be supported by these circles. Now let's consider another point, P2. And let's say that also for P2, the number of distinct distances is at most T. Okay, so we have another point. And again, we can find all the points of P lying on T circles centered at P2. What it means is that the set P must lie on the union of this and the union of this. So each point of P must lie on an intersection of 2 circles, one from this family and one from the other family. So from this picture, it's easy to see that we can choose. So if we want P to be of size n, we can have T be square root of n, right? I wanted someone to say. And if we will have square root of n circles from centered at P2, let's take any square root of n circles centered at P1, the intersection will produce n points, right? And if we take these n points to be our set P, then the number of distinct distances that will be spanned, so the union dP1 of P will be of size roughly square root of n. Okay. And now what happens if I add a third? If I add a third point, P3. So this is really the question. So now again, let's say that the number of distinct, I don't want to write it again, but the number of distinct distances spent between P3 and the set is again T. So now I have a third family of T circles. And now each point of my set P will have to lie on three circles, one from each family. And the question really is, can I still have here n T squared points in this intersection, or do I have to have less? One way to see this problem. So it turns out that in general, I will have to have less than T squared. But if those 3 points are collinear, then I can choose the third family so that it still intersects. So now let me write the statement that I want to. So I'll erase this. Claim. I read it as a claim, but actually it's a theorem. So I think that with this bound, Shari and Shoy Moshi maybe. So again, the best exponent will be with the recent improvement of Shoy Moshi and Zahl will be better. So they show. Okay, let me write the claim. So the claim is that D, right, this union is of cardinality at least some constant times n to 7/12, unless the 3 points, unless P1, P2, P3 are collinear. And proof sketch. So how are we going to prove it? I can reduce it to the Elekes setting. How should I reduce it to the Elekes setting? So I want to find some polynomial and apply Elekes and Sabo. Where did I? Okay, it's here. Find the polynomial of 3 variables and apply Elekes Sabo. So what would be the polynomial? So the idea is this: if we take a point in P, let's call it Q, and we check what is the distance between P1 and this point Q, let's call it X. And then we check the distance between P2 and this point Q, let's call it Y. If I'm given X and Y, I don't need to know Q. From X and Y, I can reproduce Q. And then after I have Q, I can compute the distance between Q and P3. Let's call it Z. Right. So from this, it's not hard to see that there is a polynomial. So there exists a polynomial of 3 variables such that if X, Y, and Z are distances of point Q, there are 2 from P1, P2, and P3 respectively, then this polynomial doesn't have to be 0. And so just does the computation there and tells me what Z is in terms of X and Y. That's the polynomial. Okay. Okay, so now I have this polynomial, and what they do is they consider the intersection of the zero set of F with the grid D Cartesian product D Cartesian product D. So D, remember that D is the set of distances that are spent between the 3 points and the set P, the large set P. Okay, so what do I know about this intersection? So on the one hand, I know that there are n points, right? N points here. And each point of P will produce a triple XYZ that zeros the polynomial F. So I know that the intersection is of size at least n. And on the other hand, I know by Elekes that this intersection cannot be too large. So up to a constant, it must be at least cardinality of D to the power of 12/7. So this happens unless the surface F equals 0 is special. In Elekes and Ronyai, we had two alternatives. So this is what happens if the first alternative holds and there is still the other alternative. So if it's not this, we have this inequality, which gives us that size of D is at least some constant times n to 7/12. Okay. So this we did without knowing anything, and now maybe the challenge is to show that the zero set is, the surface is special. We need to understand for what choices of P1, P2, P3 is special, and Sharon Sharmashi showed that this happens. Okay, I'm not sure if they knew it before, never mind, but one can show that this is special if and only if P1, P2, and P3 are collinear. So any questions about this? I think I'm going now to move to the Hausdorff dimension setting. Yes. Not so easy, but okay. Don't ask me to do it with this one.
So this somehow reflects the idea with the circles.
Yes, so this intersection is exactly the number of points that are in the intersection of three families of circles that are centered at 3 points. So this is exactly the example.
Yeah.
I have some questions where the answer is like the points lie in a low degree curve, or like that kind of the special case is not a linear of kind of this.
So which points? You mean the set P, the large?
This is like everything is like very or either grid or like linear or like I'm trying to ask if there are like questions where the natural answer is something of kind of a low degree surface, low degree curve, or.
So let me think. So I mean, the points here rely on a line, right? But do you mean the large set maybe, or?
I don't know. I'm just trying to understand the flavor of the.
So usually what happens is that we have some gap and then we add more constraints and say maybe you can improve it, and then we can't really use the extra information that is given us. But like I'm trying to think of, so you were saying, I mean, if the large set P would lie on some curve, then you would have.
Yeah, maybe in higher dimensions.
Maybe
not in dimension.
So in higher dimension, if you would take, so you want some constraint, you want something. So I guess that if we go to 3 dimensions, we would need to take 4 points. Otherwise, the intersection of 3 families of sphere would produce T's cubed points. And so let me think. And this will be a polynomial. This will give you something. We have this. And it will have coordination 1, right? Whenever we have three distances, we can say what Q is, and then we can compute W. And we know here that either you will have, so you can have a certain result here, where you will need to characterize as the case where this surface is degenerate. I'm not sure if it will, I don't think it was done. Okay. I mean, it makes sense, and these techniques will work.
Okay.
But yeah, I'm not sure. Maybe later we can try to understand more what to. Okay. But there are questions where the points are, when they are just in the plane, it's really hard. And then when you restrict them to a curve, you can say more. So there are other examples if you want to. Okay. But so, okay. So these were examples of questions in the discrete setting. So the sets are finite. Let's look at other questions that might look like some analogues of these, but with infinite sets. Hausdorff. So you don't really need to know what Hausdorff dimension is, because the proofs will work in a third setting introduced by Katz-Tao called the Discretized setting, which is something in between the infinite one and the finite one. Okay, and I will introduce it next. So first, I just again formulate some questions and tell you results. So it's going to be again such a list. Okay, so the first one is Falconer's conjecture. Falconer's. So what it says, so the conjecture, we have a set in the plane, or a set. It has Hausdorff dimension. So whenever I dimension, I mean Hausdorff dimension, it's Hausdorff dimension 1, and the conjecture asserts that the dimension of the set of distances, I just call the set here E instead of P, but it's the same thing. Set of distances will have dimension 1. It's a conjecture. It's still open. And Falconer proved that this dimension will always be at least 1/2. And this 1/2 was improved by Bourgain to be 1/2 plus some constant C. Second. So people worked on this problem. There are all kinds of results. So in some results, one may assume that the dimension of E is slightly larger than 1, and then maybe prove that the dimension of the distance set is 1. But I'm going to mention result of Bourgain.
This 1/2 also with fixing 2 points and this is done by the Falconer proof. Is it also easy?
I don't know actually. This is like the middle setting is the one that I know the less about, because I worked on the discretized setting. So yes, I'm not sure. Maybe I should put that.
Delta of E.
Sorry, the dimension.
Yeah.
This is what Falconer proved in the original paper, and then a theorem of Bourgain. But Bourgain used the reduction of Katz-Tao, so I write the discretized setting, which I'm going to give more details about in a moment. He showed that the So again, E is of dimension 1, and the distance set will have dimension 1/2 plus some constant C. So the dimension of the distance set is for C, positive C universal. So independent of E. Okay, and the pin version also makes sense here. Okay, so this is one thing I wanted to mention. And I think that the last one before I introduce the new result is about projection. So projection theorems.
Is 1/2 plus C known for the pin version?
What here?
Yeah, is 1/2 plus C known for the pin version of this Falconer?
No, so I don't think so. No. Okay, so here again. If we have a subset of R2, its dimension alpha between 0 and 1. And now let's look at this set. So we look at the vector on the sphere, so it's a direction, and we consider the projection of this set E, onto the line spanned. So we have U, we have the set E, and we look at the line spanned by this direction U, and we project E, get here the set. And so for some directions, the dimension of the projection of E might be small. So the dimension of the projection is most alpha over 2. Okay, so let's look at all of these directions such that the projection is really small, so this dimension. And what Bourgain proved is that this set of directions will have Hausdorff dimension 0. Okay. And it turns out that, so there's an example of Kaufman and Matila that shows, so shows that alpha over 2 cannot be replaced by any alpha over 2 plus C. So if you, instead of alpha over 2, you write here alpha over t plus any constant C, one can find an example of a set such that this direction would have positive Hausdorff dimension. Okay. And another theorem of Shmerkin in this spirit. The following, we now have a set E, again dimension alpha, and alpha is between 0 and 1. And we look at something similar, but now instead of projection, we take some nonlinear map from R2 to R. So I'm stating it, so it has some more general results, but specifically it works for the distance function. So let's look at all the points P in R2, such that the dimension of the distance set from P to the other points in the set is at most alpha over 2. And Shmerkin proved that this set will have to have Hausdorff dimension 0. Okay, so very similar to Bourgain result, but with this replacing the. And again, it turns out that one cannot improve, cannot replace the alpha over 2 by alpha over 2 plus c. So an example. So it's based on Elekes example. So I'm thinking whether I should write the example or not. Okay, I'll write it down. So we have. So I want to show an example that shows us that here we cannot have alpha over 2 plus c and still have a dimension 0. So let's take A, B, and the set S in the interval 0, 1, such that dimension A times B is alpha, the dimension of S is positive, and the dimension of A minus S times B is less than alpha over 2 plus c. So you're going to ask me how to find such set. So this is from the example of, this can be found in the paper of Kaufman and Matila, so I'm not going to give the details here.
A minus?
A minus SB, where S is for, so for every S. A minus, now it's little s.
Okay.
So existence okay, and then if we take now our set E, the set of points QAB, I'm going to say what QAB is for A, B, and B, where QAB is just A over 2, where we do 1 plus B minus C over 4. So these are the points, and K will be yes Cartesian product with 0, so points on the x-axis. So we have the dimension of E alpha, the dimension of K is positive, and I want to say that the dimension of the set of distances for each point in K, if we take a point in K, look at all the distances between this point and the set E, the set of distances will have dimension more larger than alpha over 2 plus c. And since K have a positive Hausdorff dimension, this means that we cannot change alpha over 2 here to alpha over 2 plus c. Okay. Okay, so now, I mean, after we have this, we can just do the computation. We'll just write it down quickly and can move on. Just so for every, so okay, what is the distance between a point from K?
What does the set in this Kaufman Matila example look like?
So it's pretty complex.
Okay.
It's like it's not
some specific structure.
Yeah, they have a construction there. Okay. So S0 minus QAB, the distance is S squared plus 1. Okay, let's do the computation. So S minus A over 2 squared plus 1 plus B minus A squared over 4. And this gives, so S squared plus 1 minus 2 times S times A over 2. So it is minus a, let's write it like this, b, and a squared over 4 is cancelled with this a squared over 4, it's this. So when this point is fixed, this is just a constant. And here, if we go through all the points, all of A, B, and A and B, the dimension of the distance set between the point S0 and the set E that we defined is the same as the dimension of B minus SA. Did I write here B minus SA? No. Just changing the names of A and B, which we know is more than alpha 2 plus C. Okay, maybe it was clear, but it's just a specific construction. Where? No.
Less than alpha, right?
Sorry?
Less than alpha over 2 plus C.
Less, yes, thank you. Thank you. Yes. Okay. Thank you. So each of these points in K will be in this set and this one. Yes, thank you. Okay, I see, I'm looking at the clock, that's my problem now. So let's see, I want to state our results. And then we will take a short break and I'll talk about the proof and the discretized setting of Katz-Tao. Okay, so let me just mention the new results. So what do we prove? So even if you didn't follow the details of this example, it's not that important. We have this theorem of Shmerkin, and we see that this example shows that you cannot change here alpha over 2 to alpha over 2 plus C. So so maybe, can we still say something? So what we show is that, so we can't show that this set has dimension 0, but we will show that this set has a special structure. So, yes, and if I didn't say so, everything is based on a joint work with Josh Zahl. Okay, so theorem is the following. So we have alpha between 0 and 1, and we can find a constant. There exists a constant such that sorry, alpha and 2, 0 and 2. Is not 2, dimension of E is alpha, it's Bourgain, of course, and then we consider this set, the stigma from Shmerkin theorem, all points in R2 such that the dimension of the set of distances between P, this is 0, and the set E is less than alpha over 2 plus C. This set, we cannot say its dimension is 0, but what we're showing is that it is flat. So then the set is flat, then you need to define it. Okay.
So it's less than 2.
Yes, it says. Okay. So what it means to be flat? Flat. I don't want to spend time on writing the definition. Let me. Okay, I'll write everything. Okay, so the definition. So E. Bourgain. Curve. So flat would mean that there are many triangles that are flat, but the area of these triangles is very small. But what do I mean by small? I mean, what are the parameters that I can use? So we first define what it means to be a curved set. So a set is called curved if there exists some constants, so a positive number beta, C, and a probability measure mu so its support needs to be contained in it, such that if we look at all the triples, P1, P2, P3, in E cubed, and such that the area of the triangle that they span is smaller than R, the measure here needs to be less than this constancy times R to the power beta for every R. So there are not too many triples that have that span thin triangles. And if it is not curved, then we call this if E is not curved, we say it is flat. So something pretty technical, but gives some bounded number of thin triangles in this sense. And so a corollary from this theorem is an instance of the pin Falconer. Hey, it's one way to see it. So if our set has a positive dimension and it is not flat, then it's impossible that all of our set will be here, right? That the dimension of all these, all of them will be small.
Are there easy examples of curved sets and flat sets that you could give?
Yeah, so flat would be like points that are contained in a line or in a union of lines. In curved, so now it's going to be an example. So one example of curved set is if it is contained in a curve which has non-vanishing curvature everywhere.
Okay.
Somehow to be able to bound the number of triples that are. Okay, so yeah, so the corollary. And I want to think of it as an instance of the pin. Okay, I won't tell you that, but the instance of a pin Falconer. So if our set happens to be contained in a curve gamma, so gamma smooth and non-vanishing. Then what do we know? So we know that the dimension of all points P that are in gamma that span a distance set with dimension of alpha over 2 plus C. We know that this set has dimension 0 because if a set contains, so let's call, I need the letter, like the name. Let's call this set K. Okay. So K is the set of all points in R2 such that they span, if we look at the distances between these points P and our set E, this has small dimension, okay? And we know that this set must be flat. Okay. So what it means to be flat, it means it is not curved. A set that contains a curved set is itself curved. Why? Because of the definition. In the definition, we can take a probability measure that is supported on our set. So we can just take a probability measure on a subset, and it will still work. So if something contains a flat set of positive dimension, we can already have it. If a set contains a curved set that has a positive dimension, then it must be curved itself. Okay, so if this set K will contain a subset of gamma which has positive dimension, K will be curved itself, but the theorem says that it must be flat. So it cannot contain a subset of gamma with positive dimension. So this set K, when we intersect it with gamma, it must have dimension 0. And since we started with a set E that has a positive dimension, there will be a point in E that is not here, it is not in K. So this would mean that there exists P in E, because E is contained in gamma, such that the dimension of this distance set is at least alpha over 2 plus C. I don't know if I wrote strict inequality or not. Not important because C can change C. Okay, so this is one result that I wanted to mention. The second one is a Elekes and Ronyai. And I know it looks like a list of problems, but I promise you that in the next hour, I'm going to talk about the proof, so you will get a flavor of what's going on and how we prove it. Okay, but just one more statement. So about dimension. So we're dimension expanding polynomial. The theorem. If you remember the Elekes and Ronyai theorem from the beginning, so we prove exactly the same thing, but for infinite set, so in this setting. So f is a polynomial of 2 variables. Then either first option is that for any 2 sets A and B in R, or L, let's see, both have the same, not let's say, we prove it with the same dimension. Something you got me, no? The dimension of A is the dimension of B. They don't have to have exactly the same dimension up to some epsilon, it's okay, but we don't try to have different ones. Probably something can be done, but this is what we show. So the dimension of both, let's say, is alpha, and we have that the set f of AB must have large dimension, so its dimension is at least alpha plus some constant. The constant will depend on alpha, not on the degree, not on f. And the other alternative is that f is special in the usual. So this is 1 and 2, or 2 f has this one of these special forms. So if we started with a polynomial, we will have this form. If we start with an analytic function, we still have a statement, but here the form will be with an analytic function. So we have something as an analytic function.
But it's the range of P plus Q range of P.
Yes. Yes. Also in the Elekes setting, you can change it so that it is of this form, just invert one of the functions. So it's, yes. And okay. So this is the list that I wanted to make for the Hausdorff dimension setting. So what I want to do next is to introduce the in-between setting of Katz-Tao, so a discretized setting, and tell you how it allows one, this is what Katz-Tao showed, allows one to prove things in this discretized setting and then use them in order to prove this statement in the Hausdorff dimension setting, and then tell you concretely about some of the proofs, the new results that they introduced. So break, I guess you want to break. So yeah, so we talked about the problem in the discrete setting, some analogues or problems that remind us the question in the discrete setting in the Hausdorff dimension setting. And now let's talk about the third setting. Third and last is the Katz-Tao discretized setting. So I'm not going to list problems here, I just want to introduce this. So
It's like the curve is smooth, and the amount of smoothness is the standard ratio.
you need to be able to compute. You had a break of 10 minutes. You need to be able to somehow to bound, like to compute like the area of this triangle and to bound it in terms of the, yeah, I need to check exactly what I guess like infinitely smooth, everything you want. I mean, I just wanted some instance to talk about. Maybe there are more.
Okay, it's not.
Okay, so what is the Katz-Tao discretized setting? So I might introduce it in more detail in the what is seminar and give some proof, but now I just want to like present it. So definition. So we have a set. This time we look at the unit cube, it's 0, 1 to the n. Okay, I write it with the general dimension just because I might use it in the plane or in R, but it's not higher than that. And so our set is a union of delta balls, so balls of radius delta, just shorter to write it like this. And so already we see it's sort of finite. We can like look at the centers of these balls. And of course, delta is positive. We're in, yes, we're in a compact domain. You can always move to a.
I'm just asking your definition.
And let me think about it, okay? Okay. I'll answer in a second. So alpha is between 0 and n, it's positive, and we have parameter tau. Think of it as a small one. Actually, you can ignore it, but this is part of the definition. But so we say that E F delta alpha n set. So I define a delta alpha n set, and this will replace the set of say of dimension alpha. So alpha should be more or less the dimension. So if the intersection of E with, so I think that for the definition you don't need to say finite, but when we use it, we can always move to finite unions. I think that here, okay, let's see what the other condition is. So the intersection of the set E with any ball of radius R is at most delta power n minus tau. So again, you can ignore for now this tau, it's just small refinement, making this condition to be a weaker requirement, which is good, less restrictive, times R divided by delta alpha. For every R between delta and 1 and X in Rn. So how do I think about this definition? Then maybe I will answer you better. So the way I think about it is that, first of all, if we put R, take R to be 1 or 2, we take the intersection of the set with with the ball that contains the unit cube and dimensional cube. So this inequality, what it would tell us is that, so now when I use absolute value, I mean volume, standard volume in Rn. Okay. So the volume of this intersection is at most, so here it says delta to the power of n, which is more or less the volume of a ball of radius delta in Rn. So this is the volume of a ball times a certain quantity, but if I took R to be 1, so I want to think about it is that E, so need delta to, so more or less delta to the minus alpha. Delta balls So this intersection, so this set E, the volume that it has is at most delta to the power n times delta to the minus alpha. So if I want to cover it by delta balls, I will need at least this number of balls. This is how I think about it. And the other condition, when when I take a general R, how do I see this? So I see it as a non-concentration. Condition. What do I mean by that? So first of all, I have a set, and I think about it as a set which is a union of delta to the minus alpha delta balls. But I don't want these, if I have a certain number of balls for the whole set, if I restrict to a smaller ball, I don't want all the set to be inside this ball. I want it to look more or less as the big set. So for example, if we are on the line, this is the 0, 1 interval, let's divide it into, so let's take delta to be 1 over n. Okay, so the 0, 1 has, right, so intervals of minus intervals of length 1 over n. We have n such intervals, and if alpha, just to be concrete, if alpha is 1/2, so the first item here says that we need at least square root of n. So that we need at least square root of n delta intervals of length 1 over n in order to cover our set E. So we have some subset here of intervals of length 1 over n. And now when we take general R, so we restrict ourselves to an interval of length R. So how many delta intervals do we expect to see here? We want it to look like the big set. So if an interval of length R will have Rn intervals of length 1 over n, and from there we want to take the square root. So we want the number of intervals of length delta inside an interval of length R to be square root of the number of potential intervals. So when we restrict to this interval, it will look in this sense as if it is the big set. Okay. So some non-concentration. We don't want to have too many intervals of our set in a smaller ball. Okay, so
A very brief question. Is E assumed to be a disjoint union of delta balls?
so no, but you can. So instead of, okay, so this is just, you can describe E as this union, right? As a union of balls, and you need to have these properties. But if you have these properties, you can actually move to a different, you don't have to fix this union. You can replace this by a different union.
Right,
Which is-
sure, but then I don't understand the assumption, because if you're not assuming finite union, you're not assuming disjoint union, then every set is a union of delta.
So what I'm, so, right, so the
Well,
only thing is, an assumption is that
Covered by.
if you have, you can't have a disjoint point. You really need to take all of its neighborhood.
Okay, just that, okay. I see.
And when we will have 2 points that are very close to each other, to one another, they will somehow go
Right.
together inside. Okay. So this is how I think of it, and it can become formal. You can take the minimal union and with these properties. So, okay, but this is the definition that I gave, and so we can see this is. Why do I think about it as in between? Because we really have, so again, I think of it as a finite set. So we really have some finite set, but with some extra condition. Okay, and so so I'm not going to write here formal statement because usually they are very technical, but just as an informal discussion, so informally, discussion, no. So how would statement, or how to think about the statement in this setting? How the statement like. So let's think about the Elekes and Ronyai theorem that I stated. So we have two sets. We have a polynomial, and we want to look at the image of A Cartesian P under the polynomial f. Okay. So what do we have here? So we will have two sets A and B. It will be contained in the interval 0, 1. And we will assume that each of them, each is a delta alpha 1 set. Okay. So roughly, again, you need to believe me with this, but roughly union of delta to the minus alpha delta intervals. Right, with the plus some non-concentration. Assumption. So what is the question here? We have the set A. It's a certain union of delta intervals. We have B, and the union of certain interval. We can, instead of taking this the whole set, we can look only at the centers of these balls. And we have the polynomial f. So let's apply the polynomial over the sets. We can apply it over the centers. It's a polynomial. We're in a compact domain. We have a bound of the derivatives. So a ball of radius delta will move to a ball of radius smallest delta. So f of a, b. We look at the image. So first, let's consider the centers. Okay? So if f is not special, we know that the image, so we have here delta n to the alpha point, n to the alpha point. If f is not special of this additive form, we know that the image will be large, right, of the centers. So we know that the number of points here in the image will be much more than n to the alpha, right? So image by standard Elekes and Ronyai image of centers is of size at least, and so some power, so 3 alpha over 2. So we know that we have here many points. So what is new? What is the new question? The thing is that these points, they are distinct. There are many distinct points, but they might be very close to one another. And now when I try to cover them by delta intervals, I get that I need a small number of delta intervals. So the new question is, okay, we know that we are going to be distinct points, but are they also separated? So if we cannot tell the difference between 2 points if they are very close to each other, can we still say that the image set is big? Okay, so this is the new question. I'm not going to answer it. This is just something. Yeah, but when we prove that the conclusion, a good conclusion would be that the volume, here it's in R, so the one-dimensional volume of the image set is at least delta 1 minus alpha minus c. Right, so an interval is of length delta. So how many intervals I need in order to cover the image set? So it's n to the power alpha plus c. So slightly more than n to the power alpha. Okay. So I didn't write a formal statement, but we prove this type of result. Okay, so this is the discretized setting. This is how statements there look like. What does it have to do with the problems with Hausdorff dimension? So Katz-Tao, in their paper, they showed several examples. They formulated conjectures in the discretized settings, and they showed how if one proves these statements, they will imply some other statements in the Hausdorff dimension setting. And so the result of the dimension, for example, of Bourgain, improving the 1/2 in Falconer's conjecture into 1F plus C, did exactly that. So he proved the conjecture that Katz-Tao stated, and using the results, it implied the improvement for the original Falconer's theorem. So how do we move from results in the discretized, in Katz-Tao discretized setting to the setting of the Hausdorff dimensions? So they have a lemma there. It will not tell the whole story, but will give some hint about the connection between the two settings. So what they showed is that if the dimension of E is at most alpha, then one can find a covering. So there exists a family of family X delta where delta, so they show it when delta is hyperdyadic, they define what it means. You can think about delta dyadic as some sequence of deltas that go to 0. Of subsets over n such that, so we start with a set of dimension at most alpha. If we have it, we can move to a family of subsets of Rn. Each of them, so x delta, each of the sets, so x delta is a set. X delta is a delta alpha n set, the thing that we just defined. And also this family is a strong cover, strongly covers E, meaning that each element of E belongs to an infinitely many elements here. So strongly cover each delta or infinity and delta. If we have a set of dimension alpha, we can move to discovering, and they show that also the other direction is more or less true. So there's also this. If we have discovering and the dimension is at most alpha, so they don't show exactly this. They have here minus some epsilon, so something stronger a little bit in order to so this is why I have this. But more or less, this is really if and only condition. So it doesn't exactly show us how to use it, but it shows that there is some connection. And I'm going to sketch proof to one of the results that I mentioned, and hopefully it will give you an idea of how to use it in order, how to use the statement in the discretized setting in order to prove Hausdorff dimension statement. Okay, any questions so far?
Delta is, I should think of as a sequence of scales, yeah?
Yes. Okay.
Would belong to all to infinitely many, or would a stronger statement be true that to almost any in some sense, or?
Ask me in the what is seminar when I prove this. No, let me think. Yeah, I'm not sure. Do you remember?
Repeat the question.
I was just asking this. There is a stronger statement that it's element belongs to almost all. It's like.
I don't
Okay, ask me
remember
what is.
I don't remember, but I remember that in some of the directions you can replace
Hyperdyadic with dyadic.
dyadic.
Yeah, I think that hyperdyadic is just, it just shows you that you don't need all of them. You just need a subset, so it's okay to say dyadic. I mean, something strong. Oh, you're saying that if it's, okay. All right. Let's ignore. Okay, so the last thing I want to show is a sketch of proof of one of the theorems that showed some connection between the problems that I showed and also more or less explain how to use this lemma. Okay, so what theorem do I want to use to sketch? So I want to prove the theorem with the flat sets. So should I restate it? Sketch the proof. So this is the one with the, when we fix a point, we look at all the distances from this point. And if the dimension is too small, we put it in a set. And we want to say that there aren't too many, not that there are too many, sorry. So the set of bad triangles is a flat. Yeah, there aren't too many triangles that are flat. Wait, so let me just find it. Here. So E R2 Borel. Actually, we will move to compact sets, so maybe from, let me write it already. Is Hausdorff dimension alpha. And you want to say that this set of all points such that the distances in those as they mentioned alpha 2 plus C is flat if C is sufficiently small. Sorry? No. Okay. Okay. So sketch of proof. So the first step of the proof, step 1, will be to prove an analog of the problem that I mentioned in the introduction about distances between 3 points and a set. So we proved and discretized analog of the from 3 points. I hope you remember it, the one with the circles. I will state it because I want to emphasize something here. So again, we have 3 points where we look at all the distances from a certain set, this time E, and we want to say that, that for one of them, the set of distances will be large, or the union is large, right? So now we have a set X in 0, 1 square, so in the unit square, and this set is delta alpha. You don't really need to remember the definition here, it's just discretized set, so delta alpha 2 set. And we are given 3 points, P1, P2, P3, in square. And okay, there is something to write here, but let me write it in a second. What we want to say is that, again, for one of these points, then the set of distances from this point Pi to X is large. Okay, so we'll show that there exists some I between 1 and 3. It's the same as saying that the union, right? The union of 3 things, the one of them will be, right, it will be large. So there is some I between 1 and 3, such that this distance that has one-dimensional area larger than delta 1 minus alpha over 2 minus c, which is more than alpha over 2. You need to think about it as alpha over 2 plus c. Okay? So what do I want to write here? So I showed you at the introduction that when we ask this question, actually it hides a question, the more general question, as in the Elekes Sabo setting, right? And I already told you that Elekes Sabo is more or less Elekes Ronyai, and Elekes Ronyai, I told you that we have it in
Dimension, or this is?
no, this is volume, one-dimensional volume.
What is it? Is it clear that this is measurable? Or?
So it's a union. So because everything is continuous, it will be union of you start with the system.
Okay. But when you said a delta alpha 2 set, is that it is a union or contained in the union?
It is a union.
It is as is.
Yes.
Okay.
You really have to
I guess-
take all the neighborhood, all the
I guess
delta.
for every open set, there is a delta such that, because you're in a compact setting, so
For every open, again,
every open set is a union of delta balls for some delta because you're inside a compact set. So you just take the minimum delta that you can find a ball around every single point. It exists because compact.
But the idea
you can do it, but
but the idea is fixing delta. But it's
Yeah, sure. But if I give you an open set, there exists a delta such that blocked. But then you need to know what's the delta for the definition, of course, right? And it
I
changes.
mean, here it's given that X is a union of,
That's not true. Like, you can have
No,
like,
but it's a compact.
no, I mean, inside the thing, you could just take like infinitely many small balls separated.
Yeah, the set E is
Yes,
not compact.
but here it's
Nah, you're right, yeah.
here it's given that X is a
Yeah,
union of delta R, so you don't need to show the existence. This is part of the assumption. Okay, so I hope you more or less believe me that there is an analog of Elekes Sabo or Elekes Ronyai in the discretized setting and in the Hausdorff dimension setting. So we should believe this, right? So we have P1, P2, P3. These 3 points can be associated with some polynomial. We fix this polynomial, and now we look at the analog of the Elekes Sabo statement or Elekes Ronyai statement, and we should have this conclusion unless the 3 points are collinear. So this is true. The thing is that here, what we assume, so usually in these statements, we say, okay, we have this polynomial, maybe some of the coefficients are very large with respect to delta or very delta in some way, but if we take delta, so if we fix the polynomial, we take delta sufficiently small that it kills all this constant, and then we can have such a statement. This is what we usually, when we prove the analog of Elekes Ronyai, we say it holds for delta sufficiently small. The problem is that here, when we are going to apply it, for the theorem that I'm now sketching its proof, we will not be able to fix the 3 points and then take delta to be small. Whenever we have, so the 3 points come with delta. So we have delta, and for this specific delta, we are given 3 points. So we couldn't use this general theorem. We needed to go into the subtle details of the proof to understand what exactly is the requirement for the 3 points. And it turns out that if we, so what is the problem? Why can't we say that they are not collinear? Because if the points are almost collinear, almost is somehow with respect to delta, then when you look at the distances that they span with a certain set, if we don't care about differences that are up to delta, it might look exactly the same as the set of distances spanned by 3 points that are collinear, because they're almost collinear. So we need to say that they're, if we can't take delta to be as small as we wish, we'll need to say something about this, about these 3 points not being too close to being collinear. So the condition here is that the triangle has a certain area.
This is where the flatness comes.
Yeah, exactly. So they span a triangle. So the 3 points condition is that they span triangle of area at least delta the power c, where c is the c will depend on alpha Okay. Yeah, I hope the constants are, but something of this form, I think that they are correct. So if this has sufficiently large area, then we can have the conclusion. Okay. So now, as Tami said, we already see all the connections. So the second step is here just to show you how to use the lemma of Katz-Tao and go from a discretized statement to a Hausdorff dimension one. Which time I have? Someone needs to tell them that it's impossible to move this forward. Okay. I mean, every speaker mentions it. But
Probably just did this spray thing.
yeah, it's
Spikes, I don't know what it's called.
okay. But there's too many words.
Still, yeah, just use it.
But let's use this one. So. Now, okay. Now I understand what's the problem with this board. If I start here, it wouldn't come up. And if I now take this down, then the other one is not erased. That's not good. Okay. Like the attention. So this was step one. So step two. So now we really start a proof. Step two. It's the actual proof. So we're given a set E. Okay, I already restated it. So we're given a set E, it has dimension alpha, right? And we look at the set, let's call this set K. So let K, set of all points. The unit square such that the dimension of this set is at most alpha over 2 plus C. And let's assume that K is curved. And then we're going to show a contradiction if C is sufficiently small. So if C is sufficiently small, yields a contradiction. This is what we want to show. And so how do we show this? So using a Katz-Tao lemma, okay, so what do we know? We know that for each P in K, we know that the dimension of the set is at most alpha over 2 plus C, right? So by Katz-Tao, by the lemma that they stated, I can find this covering of this set. So there exists a family dp delta, d just because I don't like delta. So dp delta, I don't like this delta. Okay, this dp delta, it's a family. In the statement it was x delta. Okay, but this time for each p there is a covering of its own. So which is, so what is this family? So each of them, so dp delta is delta alpha over 2 plus c one set. And this family strongly covers that, right? Strongly covered a set of distances. So for each p, we have a set of distances. This set of distances, we assume that it has, because p is decay, so we assume that this set has small dimension, or dimension at most this. By Katz-Tao, we can find this covering by delta alpha over 2 plus c sets. Okay, so we have this set. Our goal is somehow to apply the theorem about triples of points from there. So this is what we want to do, and then we will get a contradiction. So how do we do that? So now we have a covering of the distance sets, right? But we want somehow to go back to the points. So how do we do that? For find EP delta on the points in E such that the distance between Q and P is in the P delta. So now P is fixed, little p, small p is fixed, and we look at all the points Q such that the distance between Q and P, we know that this distance is in delta PE, right? But let's take on the subset of the points such that this distance is in this element of the covering, so dp delta. Okay. So these are now subsets of E, subsets in R2. And it's not hard to see that they strongly cover E and probably have more properties. I'm only sketching the proof, so we're not checking all the details. And so this strongly E each P. And so what we do next is we find delta such that EP delta. And so for we fix P, we know that this covers E and in a strong sense, infinitely many times each item. But for certain deltas, maybe this set is really small. We don't have too many points of E here. Okay, but since it is a covering of E, we can find the delta such that this set will be large, and not only that it's large, it's large for many points P in K. So we find delta such that this is large. E is large for many points. Okay, so we have the set E. We look at the distances between P and the set E. We wrote the now E. We split it. Let's say split it. Of course, it's not a partition, but just so I think wait for a second. So we split E into some subsets of E, EP delta. And so this is a subset, EP delta. And we choose delta such that for P, EP delta is large. And now we have many such points. So this is P1, P2 also have so this is EP1 delta, and we have EP2 delta, and each of them is large. Okay. So the next thing to do is to say that, okay, if there are many points such that we can associate with
the many points is kind of a countable pigeonhole principle. So what does many mean here?
Yes, so let me think. Many would mean that the volume will be more or less, so let's think.
You're not using the strongly covered here, right? Just covered, or like I'm not entirely.
Yeah, I'm not. Let me think how would I actually reach it. I mean, I know the answer. I just want to say to think how the so we say
We want
that
to use it, so maybe.
what how the many. I'm going to stay in the sketchy.
Yeah, but the next point will make use of it also.
Somehow we move to probability measures and we do integrals, and then we say, okay, if this integral is large, then you know what I think. Okay, I need to think exactly, something technical, not true. But it would mean like almost all the points up to somehow we lose epsilon. I can tell you after that. I need to think, but then I can.
Do you use the strongly covered or just covered for this kind of statement?
I don't think we use the strongly covered.
Do you need strongly covered at all?
We will need it first of all in order to move back to. Okay, so let me first of all like finish the sketch and then ask, because this is the last thing. Don't
Sorry.
worry, everyone. I mean, okay.
You need the other direction of Katz-Tao.
Right. Eventually, I mean, it is going to contradict. So it's not exactly. It's like we didn't really use this paradigm that I showed, but like I cheated because I wanted it to fit. But I can answer the. I mean, I can give you the details, but later let's. Okay. So let's just finish the sketch and then ask me, and then I'll see if I can somehow remember exactly what we did. So we find the general idea. Right? We find delta such that EP delta is large for many points P, and since it's so large, then we can actually find many triples such that we want, what do we want? So what is the issue here? We want to apply this theorem. And in this theorem, we have triples of points, and we look at distances between these points and a set X, right? So one problem here is that here we look at distances between P1 and EP1 delta, and distances between P2 and EP2 delta, but we want it to be the same set, otherwise, of course, the segment is false, right? So the fact that these sets EP delta are large allows us to show that actually there is a large intersection of triples. We find again many triples, again many triples, P1, P2, P3, and K2, such that so EP1 delta intersected with EP2 delta EP3 delta is large. And what do we know about it? So we know that so now we have one set. Let's call it, I don't know. Let's call it X for a second, even though we want to change the triples, but let's fix for a second a triple P1, P2, P3. So we have a set X, which is pretty large. And we know that the set of distances, so the distances from P1 to X, distances between P2 and X, distances between P3 and X is small. Why is it small? Because it is contained in dP1 delta, dP2 delta, dP3 delta, and each of them is a delta alpha over 2 plus C set. Okay, so in this sense, it's small. So we found the set X, one set, and 3 points, and we know that the set of distances between these 3 points and this set X is small. How small? Sufficiently small to contradict the conclusion of this. Okay. So if the conclusion doesn't hold, it means that the 3 points must span a triangle of area smaller than delta to the C. So by step 1, P1, P2, P3, that triangle area less than delta to the C. And since we found many such triples, it means that our set K contains many triples of very small area, and this contradicts So this contradiction. What?
You need,
So there is number of distinct distances that they span is small because this is how we started. So it's the unit of the D.
when you need to contradict the structure.
So any contradiction will do.
Right.
So we assume that K is curved, and we say that if C is sufficiently small, it's a contradiction.
Yes, I mean, but
It
in
is a
this
contradiction.
sense, you can say that there are many points
Yes.
regarding the question. Many,
Oh, like what it means to be many.
Yes.
Many.
yes,
So many, so that it contradicts.
the fact that K is
Yes, but how? Like how do we? Yeah. Question. Wait, don't bring us back to. In a second, let me just finish to see. So this is the structure, and then we can try to think about it. So contradiction to K and curve. So this is the main idea, right, of the proof. Now I can ask. Now I can think about what you asked because this is what I wanted to say. So what did we really do? So we didn't really use. So this is. So any questions? Just about the structure and steps. Okay. So I cheated a little bit. Like we didn't really. So what did we do? Think over it. So since this cover is a covering of E, we know that. So I'm not. Let me think about it with often. I'm not sure.
Gosh, maybe I'll ask him. So I think I have some. So that thing over there is like for any the theorem says that for any C.
No, C
Or
would
there
depend.
exists.
There exists.
Where does the C comes from? Where does the C come from? Because in step one, where is that there
So
exists? this?
We don't really like. I didn't really explain how to prove this analog of Elekes Sabo, right?
You're not going to say that for any C this is flat, just that there exists it? Isn't that true for any C greater than 0? Maybe
No. So if C is too large, then no. I mean, you need C to be sufficiently small, and sufficiently small will depend on alpha.
I see. Oh wait, so I got it the other way around. Okay.
Yeah, but it should be for every C that's sufficiently small, right?
Yes.
There's a upper bound that depends on alpha, but if you take a C less than that, it should be okay.
Yes.
Just from,
Okay.
It's like you want to know,
You
right?
don't need to know what's the proof, just
Right.
the statement.
But you really want to know. I mean, in principle, it could depend on E or something like that. So it's important.
Okay, so where does the C come from? From that
So-
argument?
Yeah, so I
No,
guess
no,
you
definitely not. So
you start with the assumption that it's curved, which should give you some measure and should give you some C of the exponent. And that's the C you want to beat there, and that's what's going to determine your main, because it's that measure.
That's what
comes from
I'm-
the curve.
Yeah.
wait. So this, okay. So we didn't prove this theorem, right? We just said that, okay, we expect we will need some condition here, but we need to prove this Elekes Sabo analog, right? We don't have it. So the way we prove it,
So
I
yeah,
didn't tell you really about how proving this, and this you will need the specific C.
this is the C from the condition in the rectangle. So
If it's, you're saying,
this is self-contained, like there's no C that arises from here. If P1, P2, P3 span a triangle of area delta to the C, then
no, so we will need, no. So there are more, so let me think if we could, so no, that's not the only place that we, I mean, if we had like a general, let's forget about this triangle, let's just take another polynomial, right? We will still have some expansion property and we will still have some constant here, C. right? So this condition will come from, yeah, when we apply the theorem here, then it comes from this, then it turns out to be the same C. But, okay, so it's the same number, but what does it tell you about the proof? So now I ask your question. Now I think.
No, okay, so I'm trying to understand, I'm just trying to understand where, first of all, if do you use strongly covered anywhere and how do you use it? And I guess yeah, so I'm not sure where you lose this.
Yeah, so I think, so now I think, so first of all, the fact that this is here is just because, I mean, we need to get into this. So, okay, so we need to use the fact that it's strongly covered. It strongly covers the set. And so I can tell you what technically we have. So we have some sums, right? And somehow we say, okay, if this sum is large, then one of these elements must be, I mean, we have something very technical. But I have to
just don't, I guess maybe I just don't know the flavor of these arguments, which is why I don't understand why the fact that every point is infinitely many times covered gives you this. There is where you lose in the dimension, or in this type of argument, or that's what I guess I don't understand so much.
So so you're saying why would you need such condition that every point is covered infinitely many times? That's the.
I'm trying to understand how that is related to this. Is this where the C kind of like?
No, it's unrelated to the C. It just allows you to take a point of a set of Hausdorff dimension alpha and somehow split it into a union. You want something to represent the original set of dimension alpha. This is the condition that you would need. That you can go back from this family of sets into the original set of dimension alpha. It has nothing to do with this C.
So at some point, so where does C come from?
C comes from the proof here.
No, right? This proof has a C, and if something is C, then something C. But
yes,
where does the statement says that there is some C small enough such as, or
okay, so
where is it born?
Okay, so let's see together. So I mean, so here we get to set to where we have many triples that span triangles that have small area, and you're saying this area will depend on this C, and you want.
I think it should come from the curved assumption, right? Because the curved assumption has some exponent, and that's the exponent that you're getting to the contradiction, right? You're saying there is these triangles with large area, right? And what is large? Well, large involves some exponent.
Yeah, I think it's right. So the definition of curve will somehow.
So you need that term to be true for sufficiently small c, because the c in this step is given adversarially, right? It just says there exists some c. That's the exponent of curve. Then you want to say, well, but then I'm going to use that rather than say, but then I can get to a contradiction with the curved assumption. And then the many should be also relative to the probability measure that comes in the definition of curved. Many should be lots and lots with respect to that probability measure. That's what I understand. I don't know if that's correct, but that's how I understand the equation at least.
So you're saying we have many triples.
Yeah,
now we need this to contradict somehow the definition of curve.
So you're assuming it's curve, right? What was that curve saying? It was saying, well, there's some exponent and there's some measure, right? Such that when I look at triangles that are small for every radius, whatever, right? And
now we find some.
And then you're saying you're going to find many and many triples such that the condition fails. Well, the condition failing means, well, you need to fail with the exponent that was given to me. So that's where that C needs to be sufficiently small because it needs to be able to beat any possible exponent you could have given me. And the many should be many with respect to the measure that the curve gave you, right? So, I mean, that's what I understand from the step. Whether it's correct or not, I don't know.
But what would it mean that if I have here a C that we fixed, then the definition of curved, I mean,
Yeah, so that theorem should actually, if the intuition that I have in mind is correct, that theorem actually should be stated that it works for all C that is mode C alpha. There's a C alpha and it works for every C that's in mode C alpha.
okay.
Which I don't think it follows trivially from what you wrote, but maybe
But it
it
might-
follows from the proof. That there is this upper bound that as long as your C is less than that, then it works.
Okay.
That's
Makes
how I understand, but I don't know if it's correct.
Okay, so I'm not sure at the moment.
I don't understand fully where the strongly covered comes in.
So the strongly covered should help us to find these subsets.
Right, but at some point you mentioned that you're looking at the double integral something, and then what came to mind is that strongly covered should come from an ultra product. Is that anything to do with it or not? That's what came to mind. It does not come.
No, no.
Remember, there is some.
You want me to you want
Do it later.
yeah, I mean, yeah. If you want to stay it, I'll show you the actual, I mean, it's just like 2 lines, but.
No, because if it came from an ultra product, then I know what are the 2 integrals, but since it doesn't come, then I don't know where it comes, how you leverage that, but okay.
Remember in this Katz-Tao lemma,
No, but-
they use this strongly covered for the other direction. I think there is some one can tell you argument there.
But we don't really use the other to get a contradiction right away.
Right. But
And-
maybe
But it's like. Yeah, okay, I'm not sure. But now I know what to think about when I give this talk next time. Yeah, okay. But if you want, so let's like let people go and then I can check and tell you because it's.
If you'll miss lunch, you should do that.
I can.
It's like this is.
I have a free lunch. Okay.
And even.
Now it's even more. It's even more. Oh, if it's free.
Yeah.
Okay, so up to this, okay. Yeah, I
Okay.
think this is what I wanted to tell.
Maybe let's thank her.